Thank you, Eli. I really want to thank the organizers, and especially Eli, for inviting me to talk about my favorite subject, organic light-emitting devices. And hopefully, if you don't have an OLED display in your pocket, by the end of this talk, you will. You just rush outside and buy one. This is really quite an exciting revolution. I'm going to talk a little bit about the history, but because there's a lot of young people in the audience and active researchers like myself, I want to talk a lot also about the remaining issues that are confronting this technology. It's by no means finished. So I'm going to start off by giving a little history of OLEDs, and particularly electrophosphorescence, which has really created the revolution. What happened next, and I'll show you some rather nice demonstrations of OLEDs that you see around you in your life. And then what are the big challenges? I'm going to talk about two. There are many, but getting all the light out. This is a true optics problem. It's a hard optics problem, which I like to say you're smart by being stupid, in the sense that everything that you come up with for displays and for lighting has to be a very, very cheap, inexpensive, scalable technology. So you have to think at a really simple end of things, but you have to be very effective at it. And then finally, I want to talk a little bit about excitonic damage that goes into displays. This is arguably the biggest and most complicated and highest value problem in organic electronics today. How do we make organic electrophosphorescent devices that radiate in the blue have a long lifetime? And then a little bit about what's the future. So this is where it all began, really. The history of organic electronics goes back probably, at this point, 70, 80, 90 years, depending on where you started. But what started the generation of displays that we see today started in Kodak with Ching Tang and Steve Van Slyke. And they made a little bilayer device. It was small molecules, which mean we deposit everything in vacuum. They put two sort of electrophotographic materials, because after all, Kodak was a chemical company which was involved in photography. And they use a hole conducting material, something similar to this tertiary diamine. And then on top of it, they put ALQ, aluminum trisquinolate, and it is an electron transporting material. You put on a low work function metal, ITO on the other side, you put in charge, and you form a molecular excited state on the ALQ. And this is, the molecular excited state is an exciton, and they got light out. And it was beautiful in green. Here's the photoluminescence and the electroluminescence curve of a similar device to what they made. And it was very exciting. But the efficiency, the external efficiency, was only 1%. And this created a challenge. It started, particularly in Japan, some companies started to explore the commercial viability of such a illuminating device, because this could obviously be used in displays. You would just have to change the emitting material to get different colors out. So how do we get from 1%? That was really the question. So let's look at the quantum efficiency of a light-emitting device. This is the external quantum efficiency, which is really the internal quantum efficiency times the outcoupling efficiency from the glass substrate. And you just have some factors here. And one of them is the charge balance factor. Well, the Tang device did not control that, but that was kind of a simple matter to put some energy barriers around the emitting zone. You have the fluorescence efficiency. These chemicals are fantastic. A lot of them give 100% fluorescence efficiency, but the real crushing problem was the singlet spin ratio. So when you put in an electron from one contact and a hole on the other, you form an excited state. I'll show you this in the ensuing view graphs. But as it turns out, from just simple statistics, 1 in every 4 electrons that's injected forms a singlet state. And 3 others form a triplet state. Again, I'll go into this a little bit more in the future, in later view graphs, but that means that basically only 1 in 4 electrons can generate light because only singlet states are spin allowed to come to the ground state. And so it was wasting all of this energy. And then on top of that, there was a total internal reflection in the glass. By the time you're all done, they were getting 1%. So I want to talk now about the process of changing that and how we get to much higher external quantum efficiencies. Today you can make devices rather routinely, if you use some outcoupling, at about 70% external quantum efficiency. So I first of all want to define what is phosphorescence, because we're talking about electrophosphorescence, which means electrically excited phosphorescence. And I like this. This is a true chemical text definition of phosphorescence. It's emission that has observed a noticeable delay after the end of excitation. And I think there's probably a lot of people here doing femtosecond and picosecond spectroscopy. So a noticeable delay depends on who you're talking to. So I still like it. It's classic. And you go, Wikipedia, which is the source of all knowledge, all human knowledge, you will find this definition. I think a better definition is as follows. Perhaps a better definition is emission whose time scale is controlled by triplets rather than singlets. That is phosphorescence. And all we have to do, therefore, to understand if we have a phosphorescent emitter is to measure the decay time. And there's a whole bunch of things that fall into triplet-controlled emission, electrophosphorescence, which I'm going to talk about, delayed fluorescence, singlet fission, triplet fusion, et cetera. So let's go back to this problem of the Tang device. And it's really shown here. So this is a 2-level system you can consider to be the emitting molecule. And you put an electron in a hole, so there's a hole sitting here and there's an electron here. And you can see that this spin antisymmetric state is quantum mechanically allowed to decay in probably around 1 to 10 nanoseconds, let's say. And it's very efficient. But, all right, so that gives rise to fluorescence. 3 of the remaining states, because the electrons are injected randomly, so we can't control the spin, go into spin symmetric states. And these are not quantum mechanically allowed to go to the ground state because the ground state is a singlet state. So this gives rise to phosphorescence. It's slow, inefficient, et cetera. But if you do this little trick that my colleague at the University of Southern California, Mark Thompson, and Mark Baldo, my student, and myself got involved in, is you put in a heavy metal into the middle of the organic stuff, the ligands that are emitting, and you get spin-orbit coupling. There's a lot of orbital angular momentum of a heavy metal, and there's the spin. It couples to the spin of the excited state on the ligands, and all of a sudden, all of these states become radiative, become spin allowed because of L dot S coupling, and the singlet state immediately transfers over to the triplet manifold as well. By that same process of spin orbit coupling, you get intersystem crossing. So all of a sudden you get 4 for 4. We started out with our first molecules using platinum-based compounds, platinum octethyl porphyrin. And the spin orbit coupling is not very strong because the exciton sits quite localized on the various ligands. So these are the ligands, the light-emitting ligands around the edge and the periphery of the porphyrin. So you get something which is called ligand-centered emission. It does couple to the metal. By the way, this coupling is very strong. It goes as the atomic number to the 4th. So iridium's great, platinum's good, osmium, you name it. If you've got the money, we've got the atom. But the iridiums actually couple the excited state couples right to the central metal, and so you get a metal ligand charge transfer, MLCT. I got that backwards. Metal ligand charge transfer, and that's very highly hybridized state that is very fast. You get about 1 microsecond triplet lifetime, and it's extremely efficient. So then you turn this concept over to the industrial sector. These are just several years ago, Universal Display Corporation, which holds the patent IP for all of these phosphorescent materials. You just start changing the ligands, and this is the beauty of organic electronics, is by subtle changes to the carbon, hydrogen, nitrogen, the structures around the heavy metal. These are all iridium complexes. You can do this in blue as well. You go from the deep red through the greens and to the deep blues. And all of them can be 100% internal quantum efficiency. To make a display, all you need is to have a blue, red, and green chromophore, and you're off to the races. This is just a chromaticity chart. What you want to have is the largest possible triangle that defines the color gamut. If you're into photography, you know this stuff well. And so green is, of course, the hardest because it's really easy because of the sensitivity of the eye to pull down from saturated into here. But right now, the color gamut of OLED displays brings you up at least into the NTSC color gamut standard and beyond. And these are just photographs of 1 centimeter square devices with small variants to the molecular structure. And if you mix them, you can get whites. So you now have at least internally efficient 100%. So you could think about making extremely efficient lighting. So now let's move to displays. Now that we have the colors, how do we make displays? So here's the incumbent, rapidly losing its grip, actually. In mobile, it really is getting, it's starting to become, it's still the largest mobile display technology, liquid crystal display, but it's projected to probably fall below 50% in a year or two. Basically, how an LCD works is you have a light source, very often a fluorescent tube, and you have all of these polarizers and filters. What happens is you have a light source, and then you have liquid crystal light valves with color filters somewhere in the mix, and then you look at the output. The problem is it's because of all of these elements, it becomes quite expensive. It is also angle dependent in terms of its viewing. It tends to be slow because you have to move entire molecules. It's a color subtractive display, so it doesn't have a good contrast ratio. We don't notice this because we use a lot of displays. I can tell you I notice this every day. And I have my LCD sitting beside a OLED TV in my office, and the difference is dramatic because you don't get really solid blacks because light is always leaking through. And it's energy inefficient because you're basically throwing away most of the light. They're about 3% efficient. So if you go to an OLED display, there's two types. If you have a mobile appliance, such as a tablet, electronic tablet, or you have a cell phone, very likely you have an OLED display, and that OLED display will consist of a red, green, and blue pixels side by side. That's all there is to it. You do need in truth in advertising, you need a circular polarizer in the front simply to keep sunlight from completely drowning out the display. You don't want to have that reflected light coming back at the eye. But it's really just to keep out reflections. So that's just direct emission. If you have a TV that's an OLED TV, LG is the main manufacturer of these things. They use white emitting OLEDs, and then on top of them they put color filters. But unlike an LCD, when you turn off that pixel, it's off. So you get a very solid black. These things are fast. They work on the order of, well, tens to hundreds of kilohertz of response time by the time you put them into a display. The viewing is completely angle independent. These are Lambertian sources. The thing is thin and flexible. If you were paying attention, the consumer electronics meeting in Las Vegas in January, LG showed a television that's a 65-inch TV, an OLED TV, and it's in a box. 65 inches, approximately 65, 60 inches long, little box, and you push a button, and this thing just rolls up, nice and thin. And they're energy efficient, because you only put out light where you need it, when you need it. So this is what's become of this technology. Today, this is a little bit of an old chart. It's display search. Surprisingly, it's relatively accurate. I think the OLED display business was about $20 billion in 2017. The remarkable thing is that Samsung, which is the main panel maker, although there are others, for mobile applications, they have 1/3 of the entire mobile application market, or the smartphone market. They turn out 1.5 million of these displays per day. So when you think about that, you know, this is like the McDonald's hamburger sign for Galaxy phones. I'm just estimating. It has to be more than that, but if you think about 1.5 million per day, it sort of stuns me, because it tells you that Samsung is basically a logistics company. They've got to make, well, they make 1.5 million of these things today, but they also have to bring together plastic and electronics and gallium arsenide and silicon and all this other stuff and stick them into this phone per day. They have to then get them on airplanes and send them to stores all around the world. 1.5 million go into stores per day, and then 1.5 million of us go and buy them per day. So think about it. And that's only 1/3 of the smartphones that are out there. So it's just stunning. The other one is LG, and they're making 55-inch, 65-inch, and 77-inch TVs. And they're being sold by Panasonic. You can get them at Best Buy, Panasonic, Sony, Toshiba. They're called digital wallpaper, because they're about 2-3 millimeters thick. They're a lot of fun. And LG is a master at marketing. This is, I took this picture at Incheon in 2017. These, I like to call these things over here scale bars. They're about 1.5 meters to 2 meters high. And over here you have, it's actually a small OLED display. There's vast ones in actually, I think, the United Arab Emirates and places like that. This is a semicircle. So you get the same image on the other side. And because they are a master of marketing, they have on the floor a little sign which says OLED moment. So if you know about Kodak moments, they've stolen that, and this is where you're supposed to take pictures of their display. So it's a lot of fun. You know, what you see is what you get. White light is rapidly becoming a reality. It's still a little bit expensive, but you have an extraordinarily efficient white light source. These are some. It's turning out to be an architectural. You know, that's a sort of a first adapter type of technology, because it is expensive. So this is a chandelier. This is a circular staircase at Deutsche Bank, I think in Munich. You can make windows that are transparent until you turn them on, and chandeliers. And you can make flexible. This is an early style LG display, which is about 2 years old. And then you have smartwatches and so on. And then virtual reality. It's really good for that. If you've go get yourself some Oculus glasses or things, it's unreal. So that's kind of the past. I want to talk now a little bit about what are the big challenges still in front of us. And there's lots. I've just listed a couple. Getting the light out. You know, we have 100% source, but we have 20% of it getting out if we put it on glass because of total internal reflection. It's sort of ironic, LEDs, which are really moving very rapidly into the lighting market, are not as efficient internally, but they're much more efficient externally because of the ease of getting the light out. They have, and then blue lifetime. I won't really talk about cost and yield. You can see there's obviously companies that are very deeply invested in making lots of these fast. Just to give you an idea, the size of an OLED manufacturing tool for making cell phones is about the length of a football field. And I don't talk about the end zone. I mean, right, and this is American football, right to the walls. One machine. You put glass in on one end, and out comes cell phones, I guess, but, or at least displays. So let's talk about, very briefly, where does all the light go? So we've already decided we have 100% internal efficiency, but by the time you get down to it, total internal reflection in glass will only allow about 20 plus or minus % of the light to come out if your molecules are randomly aligned dipoles, which in general they are, not always. Then you have, this is a structure with waveguides. It's a waveguide structure. It's got high index materials. It sits on glass. You trap some light in waveguide modes. And finally, the worst of the worst is that you have a dipole in very close proximity to a metal contact, and so you excite surface plasmon polaritons, and they're very lossy. So how do we get things out? I call this part of the work in my lab no photon left behind. So good solutions. They've got to be, this is my point about you have to really think basics to do this because it's got to be extremely inexpensive. The viewing angle and the wavelength, as they change, it cannot change color. It's not good to have a white light source where you look at it here and it's got a good color temperature. You go to the right or left and it turns green or something. Similarly for displays. And it's got to be independent of the OLED structure. You can't put something inside the OLED itself. It's only it's 100 nanometers thick. So when you put things in here, it can cause a yield problem. So there's a lot of things that you can do, but most of them are either too expensive or not terribly effective because they, excuse me, they don't have one of these properties of viewing angle independence. So the first thing is get the substrate modes out. It turns out it's not a hard thing to do. Excuse me. These are polymer micro-lens arrays. You can make them on rollers, and this is kind of how they do it. It's a polymer. It's just put on in a mold, and they're about 5 to 10 microns across, and they put the light out. So that can draw the light out of the substrate. That's kind of the easy one to get. It's still, there are still problems with this sort of thing, and there's improvements that can be made. But basically, we get about 2x, maybe 1.8x improvement. So now we get an external efficiency of 40%. Getting the waveguide modes out is a little more complex. We don't want to make things too small. One of the things that we've been working on are what are called SubAnode Solutions. So you just, here's your OLED. It's got a metal contact. It's got the OLED active layers. It's got your anode. And underneath all of that, which comes as part of the substrate from the substrate supplier. Remember, the substrates that are being used today are glass, sometimes plastic, depends on your phone, but primarily glass. It's on the order of 0.3 millimeters thick, and it's 2 meters on a side. So if you think about glass, that's 0.3 millimeters thick and 2 meters on a side. It's like paper. Anytime you handle it, it just shatters. So handling these things is really a challenge. What we'd like to do is just get the substrate manufacturer to make glass that, for all intents and purposes, looks like glass, but it couples more light. So here's just putting in an index variation across the embedded into the top of the glass substrate, and as the waveguide light, here's the front, as it propagates along, it hits these index contrasting regions and scatters out. And they don't have to be very small, several microns is fine. This just shows polar emission patterns with the grid, and you can see the light coming out. Here's the emitting dipole right in the center of it. The diode itself, the OLED itself, is huge compared to this. Even at high-resolution 4K TV, is very large compared to this grid spacing. And here's just a calculation versus the electron transport layer thickness. The error modes for this particular device give you a 15% external quantum efficiency. Take out the substrate modes, you're up at 30. Now you take out the waveguide modes, fine, or get another factor of 1.5. The problem is that's only 40% of the light. We still have 60% to harvest. And that comes by getting at the surface plasmon polaritons. And what that is, of course, is if you have a emitting dipole, you set up basically a charge wave that propagates along the metal surface, but metal is extremely lossy, so it only propagates a couple microns before it's completely attenuated and it's gone. So you don't want to couple into those things. Just to give you one last look at how you can do SubAnode coupling of this, is you just coat basically one of those grids, but now we have the grid that has sort of topography. We coat it with metal, we put on a thick SiO2 layer, and then we build the OLED on top of it. And that allows, it's far enough away that it doesn't excite surface plasmon polaritons, and the light comes out the top. And these types of things, features, basically create a waveguide. I don't want to go into this, but it's a waveguide of varying thickness. There's areas where the SiO2 is thick and areas where they're thin, different modes in those two regions, and they just scatter out. They can't couple, and the surface plasmon polaritons are gone. Right now, like I said, 70% external efficiencies are starting to be reported. There's just a recent report out of Korea, J.J. Kim's group, who's done 80% outcoupling using similar techniques. So let me just talk about the last thing, and that's the lifetime. As I said earlier, this is arguably the highest value, hardest problem to solve in organic electronics today, because it's been around for 18, 20 years, and we haven't been able to solve it. So this just shows commercial OLED performance. I just took these off the web. These are phosphors, and basically 500,000 to 1 million hour lifetimes, no problem. Blue, if you go to deep blue, 100 hours. So you don't have a deep blue phosphorescent device in your cell phone or TV. You have a fluorescent device. It's still very short, but it's a lot better, and it's acceptable for displays, 11,000 hours. To give you an idea, 1 year of constant operation, which is sort of something that a 12-year-old would do, is 7,000 hours. So this is basically probably translates into a 5-year, maybe longer for your phone, probably much longer for your TVs. They're good enough. So this is an example of blue. It's just, I can't tell you how much fun it is to work in this field, because you make these things, and about an hour and a half later, you have a device that is just really pretty. These are so bright, the actual device is facing away from us, and you can just see the edge. This is one of the black lines, the vertical bars are contacts. You can see the edge emission, that it's kind of leaking around the edge, and the rest is just kind of reflecting off a piece of paper. This is just two isomers of exactly the same material. One is more ligand-centered, and this one's more ligand-centered, and this one's more metal-ligand charge transfer centered, so it's a little greener. So they're beautiful, but short-lived. So I'm just going to go and show you how you solve one physics problem here. People have been working on this problem for 10 years with very little success. I think the first blue phosphorescent device was in about 2000. So in 2008, as a physicist, my student and I looked at this problem and said, well, we don't understand chemistry very well, but we do understand physics reasonably well. Let's come up with a physics model and see where that leads us about defect formation and see if that then can guide the chemist somehow. So this is just a standard OLED, and the idea is you have these energy levels for the emitting guest, and you have this for the host, and if you cycle this enough time, it forms a defect, and then you get non-radiative a center there, and it just kills it. Is there enough energy around? Well, the red photon is 2 eV, the green photon is 2.3 eV, and the blue photon is 2.9 eV. And if you look at all the bonds in these typical molecules, there isn't much there that will go at 2.9 EVs. But if you have a collision between two excitons on neighboring molecules, you get double the energy. And so this was the model. It's basically an Auger type of process where you have a singlet or a triplet exciton that bumps into another triplet exciton, or maybe a polaron that is a free charge. This one de-excites non-radiatively, this one pushes up here, and we've got 6 eV. And that creates death. Okay, so I'll just show you one last thing, how we have attempted to fix it. If you have a host which is basically what we have, that conducts electrons into the emission zone, and the dopant itself is conducting holes, it forms an exciton. And because of the poor conductivity of the electrons in the host, they pile up at one corner of the emission zone. So this is the excitons are here, all the electrons are here, they all pile up here, and you get these collisions. So why not just grade the dopant, which has the higher mobility, downwards so that it becomes harder and harder for the holes to progress across the EML, and we get a graded device. And here, this was really quite remarkable. In 2014, it was the first time anybody had really shown an increase in the lifetime of OLEDs. These are running quite bright. We got about a 10x improvement just by grading the emission zone. So this model of defect formation seems right now. We and other people are looking at what are the actual chemical products during defect formation. But truth be told, 6 eV is a lot of energy to dump onto a molecule. And so we make white devices. Using this, this just shows these things with, this is real fruit, it's not plastic. And you can see the real colors. And it's a very efficient device, extremely intense. And here we have a lifetime of about 80,000 hours for white. So I can make my chairman relax. Will OLEDs dominate displays and lighting? And of course, I wouldn't be working in this if I wasn't an optimist. So absolutely. Large, ultra-efficient, color-tunable, architecturally adaptable form factor make this opportunity too good to miss. But there's still lots of challenges, and I've just mentioned a few. Lots of really good, solid, and deep physics problems. So with that, I want to thank my group. Of course, I have lots of sponsors and collaborators everywhere, but mostly Mark Thompson and his group at USC, I've worked with for 25 years. And that's one phase of my own group. So thank you very much.
So the OLEDs are doing great, except that they have a competitor, and that's gallium nitride. Both emerged at roughly the same time about 20 years ago. Now, there's a lot of investment. A lot of companies are now trying to distribute small gallium nitride LEDs across a small display, a big display. So that's going to be some competition for the OLEDs. And my spies tell me that you actually have a foot in the gallium nitride camp as well.
No, I don't. I don't think that's actually a good solution for displays. Obviously, I think we're the real competition, but it's a friendly one, is in lighting. The reason it's not so good for displays is because you're talking about placing 3 million pixels, and it's got to be done super cheap. It used to be the display in your phone was a very significant fraction of the cost of the phone. Now they've beaten that down through making millions of these things too. They're actually making money on the display. In lighting, it's a different story because OLEDs are an area source, so you need a lot of substrates. And I don't care what you're making, if you need a lot of it, it becomes expensive. But it is a very attractive lighting source that could blend very nicely with the specular lighting of LEDs. So I think there's a role for both to play because they're both efficient.
Okay, we have maybe time for one quick question.
Is there a possibility for lasers with organics?
So I suspect, so the question is there a possibility for lasers for organics? Obviously, optically pumped lasers are easy as pie. Electrically pumped, never say never. We're working on it. Other people are working on it. But it's an extreme challenge. There's so many losses that you have to contend with. Exciton, polaron annihilation. Exciton annihilation. You have very low index contrast between layers. So if you want to have a confined state, it tends to bleed over. It's easy to make a confined mode, but you have contacts around. So you have contact losses, which I've talked about. It takes a lot. So people have been looking at this for 20 years, and we'll see. There have been a lot of reports out there about electrically pumped lasing, and they have been 100% wrong.